Hello everybody, I'm Riccardo Ienco and I'm Technical Sales Engineer for Photon Technology Italy. So in our company we focused mainly on SNSPDs, so detectors, superconducting nanowire single-photon detectors, and we sell this kind of, devices and also the cryogenic devices needed for the superconductivity. So the main question, the main thing that we can think about is why it's important to have a single photon detectors. Why the photons are so important in the quantum technologies. So the photons are so important because they have a lot of properties, a lot of things that enable to do a lot of stuff. First of all, they are quantum objects. So thanks to the photons, we can observe entanglement, superposition, and other effects that are pure quantum effects. Thanks to the photons, we can encode information, both in binary way or in multidimensional way. And they are extremely easy to be generated, and they can say to us something about the process, the sources that emits the photons. So they can say to us also. They can tell to us also something about the process and the emission of this object. And they are also easily to be distributed via also free space or optical fiber. So thanks to this, there are a lot of applications where the single photons are important. First of all, the quantum key distribution. So the emission of the transmission of information via photons, via the quantum properties of the photons. We have also the quantum computing, specifically the photonic quantum computers, the quantum random number generators, also the characterization of the quantum sources, and finally, also the quantum imaging. There are several applications where you can realize the image using the properties of the single photons. These are not all the applications where SNSPDs has a role, but this is the most important one. So, the single photon detectors. There are a lot of different kind of devices that can detect photons, but there are just a few, specifically just one that can do it really well, especially in the 50-50, so in first infrared regime. And this kind of detector has the SNSPDs. In this table, we can see the differences of the performances of different kind of detectors. For example, APD, indium gallium arsenide APD, or other kind of APD, respect an SNSPD. And we can see that basically this kind of detector they have a higher efficiency, lowest dark count, lowest timing jitter, also the capability of resolve more photons at the same times. The only drawback is the temperature. So since they are they works with the superconductivity, you need to bring them at really low temperature, generally below the 3K. So you need all the cryogenic part, the electronics for this kind of detectors. So our core product, you can see here in a rack mountable way, it's formed by several parts. So we have an electronics that you can see here, and we have also a compressor for a cryostat, and we have obviously the cryostats. So the cryostat is the most important part because it's the one that realizes this kind of temperature, and we have several model of cryostats. And since there is also, you can ask why you have all this kind of models, because there's a dependence on the dependency on temperature of this device. So you need to, if you go down in temperature, some performances are higher. We provide accessories for this for the cryogenic parts. And finally, as I said, we can provide the SNSPDs. So the SNSPD is basically a nanowire that you bring to that temperature, and when photons arrive on the nanowire, you can measure a pulse, and you can say, okay, the photons is arrived to hit the detector. About the specification of this kind of object, we can achieve extremely high performances. All these graphics are at for lights emitted at 1550, and we can see that the efficiency can be higher than 98%. It's really hard to realize this, but we have detectors that can do this. The noise, so the level of dark count, so the events that is not created by the light that was assigned by your source is extremely low, sometimes also lower than 0.1 CPS, so 0.1 count per second. And this kind of detectors have also the PNR capability. So for PNR capability, the PNR capability is basically the photon number resolving capability. So the capability of the detectors to resolve more than one photons that reach the detectors at the same instant. And we can realize it basically changing the setup of the detectors. Instead using just one nanowire, we use more than nanowires, for example 4, 8, 16, 32 nanowire, and we can measure, we can detect more photons at a time. For example, 32 channels detectors can theoretically detect up to 32 photons that reach the detectors in the same time. All these parameters are really good in optical wavelength range and in first infrared, but we are working also on to moving at a higher wavelength, for example 3 micron, even further. We are in Naples. We have a demo lab here in Naples, so you are all invited to come to us if you have something in mind, you would like to make some tests. So we have the cryostat, we have the systems with a lot of detectors with high performances. So if you have something in mind, you can come to us. We can try to do our best to show you the performance or to think about an experiment. About the quantum application, we'll go really fast, but we have a lot of collaboration with both universities and research centers, and we provide our detectors for realization of the Zhuzhang quantum computer that now has more than 100 qubits, and they are trying to increase this number. We also had some collaboration with several institutional research centers and university, like Federico II University, CNR, National Center of Research in Italy, and other company like QTI for the quantum communication, where, as you can see in the plots on the left, we show that the performance of this detector are really high and has a really low level of dark count. That is two parameters that are really important for quantum communication. And we also demonstrate the performance of these detectors when you increase attenuation on the graphic on your right, and also what is the secure key rate per pulse when you change the level of dark count of these detectors. Another interesting results, it's about also to changing a little bit the setup of the SNSPDs itself to decrease more and more the level of dark count. Here we have a detector that has a level of dark count of 0.02 CPS. We simulate how far we can go in a telecommunication. We reach more or less 1,000 kilometers. About the photon-number resolving detectors, we demonstrate that they can be used as a random number generator, since the light that reaches the detectors obviously is not did not hit in a precise, because it's a quantum effect on the detectors, and also the reducing of the G2 volume in an heralded spontaneous parametric down conversion. About the photon-number resolving capability, finally, we also these kind of detectors are also super fast, so they can reach really high level of maximum count rate that increase with the number of detectors, as you can see here. So we exchange a K with a really high rate, and we with the using of these detectors, and we can see that how high is the processing speed key rate with this kind of detector. Finally, we have some project in collaboration with also the Ienco STI Institute, and where we are trying to do something new. So we are trying to realizing a polarization and polarization-based QKD. So a polarization-independent QKD using these detectors. And also we are trying to realize in this project, COPPA SHE, a system that can realize the imaging using the property of the timing jitter of the detector. So a camera that use the timing jitter of this kind of detectors. Also in this case, we collaborate in the Ienco STI project for this. Then we can offer just some new product like this one that is a super compact system that has inside the compressor, the helium tubes, the cryostat, electronics, the vacuum pump. So everything you need to start your experiment can be put inside this super compact system that is basically taught for server using. So it's really easy to put inside the laboratory without taking to space, and it's a plug-and-play system. So if someone is not interested about how the detectors works, about the cryogenic parts works, but just would like to realize the experiment, you take this really compact system, you put in your laboratory, you can start to go and realizing what you would like to do. Some future work, we are trying to using these detectors for increase the sensitivity. We would like to increase the sensitivity of this detector in the mid-infrared, especially for the free space communication, because there are a lot of problems to try to communicate from the ground to the satellite, from the satellite to the ground, because there is the atmosphere, there is absorption, there's a lot of things. So moving in the mid-infrared can be a solution. So we're trying to optimize this detector for this wavelength range. We are trying to work on enhanced QKD for the free space communication assay. And finally, we are also working on the application of some machine learning algorithm to increase the performance of the detectors itself, particularly to improve the capability of detect multiphotons. And that's all. Thank you for your attention. Here there are my emails, and I am here with the booth. So if you are interested, we'll go deeper. If you would like to go deeper in these technologies, just come there and we'll talk about.
Thank you very much. Do we have any questions in the audience?
Thank you very much. I have a very general question. Is there any saturation level limit for this kind of detector?
About the saturation of the detectors, you mean?
Yeah.
Yeah.
I mean, like more on the part of like number of photon which is coming. I'm not talking about the speeds.
Okay, so you are thinking about a situation when the detectors receive a lot of photons in the number, and okay, yes, there are some limits because the detectors has a dead time. So this kind of detectors, especially in the PNR setups where you have more nanowires that works in parallel, basically, you can count up to gigahertz with an efficiency of 40%, more or less. But yes, obviously there is a limit. If you increase the number of photons, at a certain point the detectors itself can block, but because it receives too many photons, and he will never return to the superconductivity regime, because when the photons reach the detectors for few nanoseconds, it became a normal resistive. It goes in a resistive regime. In that time, you cannot measure other photons. but thinks that we are talking about a few nanoseconds. So you can put a lot of light, especially if you have independent nanowires. It would be so you can reach the gigahertz really easy, and it's, I think, quite impressive for a single photon detectors.
Just one other question. The mid-infrared one that you were mentioning, it's 3, 4, 5 micron or 9, 10?
So it depends mostly on the materials. The materials that we use is niobium nitrate. At the niobium nitrate, it's sensitive up to 2 micron. You have to change a little bit the shape of the geometry. And we are now thinking to use other kind of materials to moving forward in the wavelength range. Yes, but theoretically there are some works realized also from MIT where they go up to 20 micron. So you can go really far.
Thank you for explaining. I'm interested in the other end a little bit. I propose, showed a lot of the performance statistics at 1550, which I guess is telecoms. I wondered how things perform when you're more in the visible, say, red to near infrared, where I guess I'm coming from a quantum sensing world where a lot of needs are there.
So the performance is in the in the optical wavelength range, basically. So these kind of detectors are extremely sensitive, okay, and they can work from 300 nanometers to 2 micron. So also in the optical wavelength range, the performance are basically the same. So you can have a detector that works, for example, 400 nanometers with more than 98% of system detection efficiency, few CPS DCR, the PNR capability. The problem is that obviously the geometry, the shapes of the nanowire cells change because the energy of the photon is different. So basically, when the energy of the photon is higher, there is no problem for the detection because it's easier to break the Cooper cover inside the nanowire. The problem is but you have to change the shape of the detectors. That can induce different values, for example, of timing jitter, because you have a different impedance in your nanowires. So the performance can be a little bit different, but in general, we can achieve this performance also in the optical wavelength range. And also these kind of detectors are super fast. That is something that is also hard to find, for example, for detectors optimized in optical wavelength range. Yes, but in general, we work from 300 to 3 micron, and we can achieve these parameters, these performances. Thanks so much.
Thank you. Let's thank the speaker once again.
Okay,
thank you, Riccardo.
So much. Thank you.